All right, so we got all of the different groups classified on the periodic table. Now I want to focus in on some more kind of whole table trends and patterns. So we're going to talk about group A labeling, and then there's a valence electron and ion pattern associated with them. And then there's a pattern related to radius, ionization energy, and electronegativity. So once we get through all these, you'd be able to answer a question like this one down at the bottom. Which halogen has the biggest radius? All right. So before we get into the group A labeling, I want to go over a definition here, something you want to make sure you know and have written down somewhere. But valence electrons are the electrons in the outermost shell, so the highest energy electrons, and they are the ones that are actually used in bonding. Um, atoms do best when, or they bond in order to try to get to 8 valence electrons. This is just an ideal number, something that makes them most stable. So on our periodic table, all right, let's see, I'm going to go up to the top here. Let's do this in dark blue. I'm going to go a little bit smaller today just to make sure everything's going to fit. But group A. All right, so we're going to label these. And one thing is there's a valence electron pattern. Increase, number goes up. And then there's also going to be an ion pattern that we'll add to this in a moment. But group A, so if you recall, I left some extra space over here in our numbering. And that is because some of these groups have A significations or A designations. So 1 and 2 are 1A and 2A, but then 3A is actually all the way over here in group 13 with boron. And then 4A, 5A, 6A, 7A, 8A. Right? So based on what we defined up here, group A, valence electrons, they increase as the number goes up. Right? And they actually match the number. So like group 1 has 1 valence electron. We know that from our notes. All right? Group 2 has 2 valence electrons. We know that from our notes. Group 3 actually will have 3 valence electrons. Group 4 has 4 valence electrons. 5 has 5 valence electrons. 6 has 6 valence electrons. 7A has 7 valence electrons. That's our halogens, so we knew that too. And 8A, the noble gases, they are super, super happy because they already have 8 electrons in their valence ring, and that's the main reason why they don't react. All right, so if you need to pause, make sure you have that labeled on there. But we want to show you this visual here. All right, so if you look at, this is just an abbreviated version of the periodic table, but if you notice the circles in red, those are the valence electrons. Those are the ones in the outer ring. So in 1A, all right, the outer ring always has just 1 electron. In 2A, it always just has 2 electrons. All right, in 7A, you can count 1, 2, 3, 4, 5, 6, 7 electrons in the outer ring. All right, and that goes all the way down. Now, when atoms form ions, right, we've talked about this, ions that either gain electrons or lose electrons, all right, they do this in a particular sort of pattern. All right, so atoms that have more than 4 valence electrons, so they're halfway or more to 8 valence electrons, they prefer to just take on extra electrons and fill their shell that way, so fill it up. So for example, chlorine, which is in column 7A, has 7 valence electrons. When it forms an ion, what it'll do is it'll grab 1 extra electron, That'll fill its shell, put it at 8, and have a -1 charge. All right. Likewise, positive ions form when the atom has fewer than 4 valence electrons. So for example, sodium is in group 1A. It has this one lonely little electron. Instead of trying to steal 7 to fill this ring and complete that shell, what it does is it gives this electron down and drops to the shell below, which is already full. All right. So when it comes to these valence electron patterns for the group A, and this just works for group A, there's too much going on with the transition metals in the center, so that it doesn't have a nice little easy pattern like this. But in group A, 1A, all right, we've got this one valence electron. All of these are going to give away that one electron. And then they are going to have a +1 charge once they lose that electron, right? Because if we lose a negative charge, that means we're going to have more protons than electrons, so we'll have a +1 charge, right? Group 2A, right, we can give away 2 electrons, or we could try stealing 6 to get to that magic number 8. It's a lot easier just to give away 2, right? So down here, group 2A is going to have a +2 charge because it gives away both electrons, so we lose 2 negatives. So that's how we end up overall +2. All right, 3A, if you haven't quite caught on to the pattern yet, right? We can give away 3 or take 5. Giving away 3 is going to be easier, so there'll be a +3 charge. What I like to do when I label this, and we're going to put this on on our periodic table too, so that you have it handy. What I'll do is write +-4, right? Because for carbon and silicon and the atoms below, it could go either way. It's just as easy to give away 4 as it is to take on 4. And to be truly honest, these guys actually don't form ions very often. Now, I write the +or-4 because this also lets me know that, hey, things might change after this. All right. So we go to 5A. We have the option of giving away 5 electrons or stealing 3 of them, getting 3 extras. We're going to go with the 3 extras. And when we gain 3 electrons, that means we have 3 extra negatives, so our charge is -3. All right. 6A, we have 6 valence electrons. All right, we're going to grab 2 more to get to 8. So we'll have a -2 charge. And I bet by now you know what the charge is going to be for 7A. And we got 1 missing spot, or 7 valence electrons. So we're just going to steal 1 more. And then 8A, these guys don't form ions because they're already there. They don't need to give anything away or steal anything because their shells are already full. All right. So let's add that on here. I'm going to make this super bright. All right, ion pattern. So just write these. Everything in the column forms this ion. We're just going to write the charge up top. All right, so 1. This is super, super, super important. All right, this is one of the main reasons why I want you guys to make your own periodic table, something that you're going to keep handy, because we're going to use this pattern for the rest of the class. All right. So again, pause if you still need to add those. So make sure you get those above the appropriate columns, the right signs, the right numbers, because this is something you are going to utilize quite a bit going forward. All right, the next thing we're going to talk about is atomic radius. So atomic radius is how far the nucleus is from its outer shell of electrons. That sounds like something we just talked about. What is the outer shell of electrons called? I could tell, right? Hopefully you were thinking valence electrons. All right. It's the same idea as just think about the atom as a circle, radius of a circle, the center to the edge. All right. Now there's a pattern on the periodic table related to the radius. All right. So just kind of looking at this pattern here, you can see that this radius increases. All right. In what direction? Now, where's the biggest guy? All right. And just so you know, this actually isn't a complete periodic table. The bottom period 7 is missing, but cesium is biggest on this picture. And right below cesium is francium, which would be the absolute biggest. All right, so you can see that the radius is increasing as you go down, so as you get more electrons. All right, and also as you go left. All right. So you can kind of think of it just in terms of as you get more electrons going down, it gets bigger. I know that doesn't quite match what's going on as you go across the rows, and that's just because as you go across the rows, you're getting more protons and electrons in like the same space, so it's easier for the electrons to be held in. But just remember that radius increases going down and to the left. All right, so let's add that on here. We're going to do a little arrow sort of thing down at the bottom here. So radius, I don't want to use orange, use green. All right. So those green arrows represent radius increasing. All right, so it increases down and to the left. And you might even want to add, as a reminder, that francium is the biggest. Another kind of related thing to radius, because I know you guys are going to have a question on it. All right, so the kind of overall trend that we were seeing, that when you add more electrons, typically the radius gets bigger. All right, so if an element has its standard radius, but let's say chlorine that likes to form a negative charge, so it adds extra electrons, what is going to happen to the radius when that extra electron gets put in there? Just kind of think logically about it. If we throw an extra one in there, what's going to happen? All right, so your radius increases. And just a kind of vocabulary review, since we get an extra electron, we're going to have an extra charge, a negative charge. All right, that's an anion. Likewise, if you go the opposite direction, all right, we lose an electron, we give one away, then our radius is going to decrease, and cats are positive. That's called a cation. Well, quick review of vocab, and then just know these patterns when it comes to forming ions. You will have a quiz question about this. All right, last two kind of patterns here. All right, so ionization energy is the energy required to remove an electron from an atom. All right, so if you look at this table, this diagram here, you can see white is a small amount of energy, purple is a large amount of energy. All right, so the most purple boxes are in kind of the top right corner. All right, things get more purple as you go to the right. They also get more purple as you go up. So we're going to add that, and let's stick with purple. All right, so as you go up, all right, a little OCD there, but I like my lines to actually be straight. And let's even get the definition of ionization energy on here. The energy needed to remove an electron. All right. So it kind of makes sense that, especially towards this end of the periodic table, ionization energy is super high. That's because over here we've got all of these negative ions. These guys don't want to give their electrons away. They want to steal extra ones. All right, which brings us to our last trend. Very similar to ionization energy, all right, but electronegativity is the ability of one atom to take an electron from another. All right, so this isn't keeping its own electrons, this is actually taking electrons from somewhere else. So you'll notice that, again, that top right corner is where electronegativity is highest, right? But your noble gases don't have electronegativity because they don't react. So they don't want to do this at all. All right, so fluorine is actually the highest when it comes to electronegativity. So let's add that trend on here. All right. Electronegativity is the ability of an atom to take an electron from another atom. I'm going to scooch that down just a little bit so that it doesn't mix in with the actinides. And now your periodic table is all labeled. So if any of this isn't making sense or you don't think you can, utilize these arrows, like the question that we had at the beginning, which halogen is going to have the largest radius? All right, so what I would do is I'm first, okay, halogens, they're in this kind of like maroonish color. So here we are. Largest radius is going to be the bottom one. All right. Now, just so you know, your periodic table in the book doesn't actually have this on here. So astatine would probably be the choice you have if this were like multiple choice sort of thing. But that's what's going on here. Okay. If you have questions, make contact.